collaborators who run experiments and help us with calibrating the models, and we always look at this as a continuous cycle. Today, I'm going to be talking more about what we do on the front of the computational cost, addressing the elevated computational cost. As I proceed, I would like to mention that the work that I'll be presenting today is done by the amazing people who you see on the screen today. Particularly for the scope of the presentation, I'd like to thank Diab, Panos, Fuad, and Habiba, who I think some of them are already joining us on the call as well. So thank you, everyone, plus our collaborators. And we have an extended list of collaborators that we don't have enough room in the screen to mention all of them. Now, coming back to geomechanics and particularly geoenergy, so with more and more attention and emphasis on applications like carbon geological sequestration or enhanced geothermal systems, there are grand questions that are being asked in terms of the feasibility. There are questions related to the economic feasibility, the operational feasibility. Is that even possible at a large scale for us to help us with the energy demand? And then there are questions related to the safety, the reservoir capacity limits, how much we can inject, the rates at which we can inject and induce seismicity and environmental effects and so on. Now, to address these problems at a full scale and in full detail as much as we wish, we need to address a very complex combination of multi-physical simulations. We have mechanical effects, fracture, thermal flow, chemical, and others as well that might be there. The other problem is the scale of the engineering predictions. And we are talking about multi-scale phenomena, both in time as well as in space. And both of which, lead to very, very demanding models. And at the end of the day, we want reliable models. We want them to be done within a reasonable cost in terms of the computational cost and even the money-wise, the physical cost. And we need validated and verified models as well. Which brings me to this: how are we going to approach these very, very expensive simulations? So traditionally, we have been looking at finite elements and other traditional computational models. They are rigorous. They've been developed over the years. We trust them, but we know that there is a bottleneck. While they are rigorous and reliable, the bottleneck can be the simulation time, which can be hours, days, or even more, or even very prohibitive. There are high memory requirements, and anyone who works in that field understands how much models can go suddenly out of proportion once you start adding more ingredients in terms of additional physics or trying to model multi-scale response. Now, over the last 5, 6, and more years, maybe we have been hearing about artificial intelligence, machine learning, and particularly scientific machine learning, physics-informed neural networks, and all of these. The question is, can they offer a solution? Well, there have been many developments over the last few years, and there have been many trials in the community from different parts of it. There are data-driven approaches. They are known to be expensive with poor extrapolation. There is the physics informed or the physics based or the physics, whatever you want to call it, approaches. They do work for smaller examples. They become much harder once you go for more complex geometries, phenomena, and so on. And then training them is a well-recognized and well-documented challenge, especially as the phenomena becomes more localized or has a high frequency and so on. There are facing also, challenges when it comes to 3D or large-scale applications. Most of the applications that we see in the literature are more of, small academic problems that, once we start expanding them, we face a lot of problems. And then comes the nonlinearity, especially when you start to model a very complex phenomena like fracture. Although there are some initial successes, but we're still far from saying that machine learning models, scientific machine learning models can work. So while they are fast, while they learn from the data and they have a lot of promise, there's still a bottleneck in terms of the accuracy, reliability, compliance with physics, interpretability also at the end of the day, and explainability. So we want models, if we're modeling a physical phenomenon, I want a model that I, as a human, can understand and reason, not just a black box that I should believe without understanding what's going on. So this is what has motivated us to start working on this I-FENN integrated finite element neural network. And basically, we're trying to get into the sweet green spot here. We're trying to get the best of both worlds, combine them together to get something that takes the advantages of both the finite element and the neural network. So on one side, we want the efficiency of the neural networks, or at least to get some of that. And then we also want to maintain the rigor and flexibility of the finite element to be able to extend this with the confidence that I'm having an accurate and mathematically and physically compliant model. So the idea is to go to multi-physics coupled problems and split the solution into two parts. One that's, one equation that's going to be solved by the finite element, and another one or other ones which can be solved using the neural networks to give us a very fast response. And the final objective is to get faster computations with a similar robustness to what we have in nonlinear finite element approaches. I'm going to start with, showing, how the idea developed. These are two applications that we worked extensively on. One is non-local damage, and the other one is thermoelasticity. In both of these cases, we are solving a coupled system. One equation is the mechanical equilibrium, the balance of momentum. And then in the non-local damage, this is the diffusion equation. And then in the thermoelasticity, this is the heat balance, the energy balance equations. When we discretize either of these scenarios, we end up with a mixed finite element setup. We start losing the symmetry of the tangent to operator. We start adding more. We start looking for more variables that we add into the solution vector, and we know that adding more and more of that will make things more complex. Okay, the idea of I-FENN is that let me take the first equation and still solve it using the typical finite element, but the second equation, instead of doing a staggered finite element scheme, I'll just take it and predict the solution of it using using a pre-trained neural network. And that way I can embed the solution of this equation into the first equation as a material variable. And we are hoping that the outcome will be a faster and less memory demanding solution. And this is kind of another illustration. So if you're doing a finite element monolithic approach, then you're solving this system of equations. So you have your variable u, say that's the displacement, and then a coupled variable z, which can be temperature, non-local damage, fluid pressure, and so on. And then you solve the whole system. With I-FENN, you are solving for the u using the finite element, and then solving for the other variable z using a pre-trained neural network. We've been working on this method for the past 4 or 5 years right now. We started from the very basic setup of having a single pin physics-informed neural network to predict a single snapshot in time. And then we gradually started growing that in the direction of fracture modeling and multi-physics modeling. And with each new paper or product that we push into the literature, we are trying to add more and more generalization. So we went all the way from a single pin at a single snapshot in time to being able to generalize in time and space for phase field fracture. And we're also including variable dynamic loading for pore elasticity and thermoelasticity. And today I'm going to walk you through some parts of that, the most important highlights along that journey, the ones that led to the most important milestone contributions. So we'll start with non-local damage, where this all started. This was our first problem. So as we said, the first equation will solve it using finite element. The second equation will get the solution of that or predict the solution of that using the neural network. This is the loss function that we used at the time. So we are enforcing the differential equation along with the boundary condition, which in this case is just a flux-free boundary condition. And then with that, we get a setup that's very similar to local damage. So ideally, I'm solving the non-local problem at the cost of solving the local problem. And then here, I'm trying to use the Gateau derivative to get the Jacobian. And you see here that in the Jacobian, I have the K, the elastic stiffness, plus the derivative of that with respect to u multiplied by another u. And then when you look at that and we try to expand it, then you see that, K itself is a function of damage, and damage is a function of the non-local strain. And then in order to get that derivative partial K by partial U, then I need to take the derivative of damage with respect to U. But then damage is a function of the non-local strain, and then the non-local strain is calculated from the network. So how am I going to calculate that derivative? Then we start doing some math, some pretty simple math with the chain rule, and then we realize that I need to take the derivative of the network output with respect to its input. So here, this term, I have the derivative of the equivalent strain with respect to the non-local equivalent strain with respect to the local equivalent strain, which is basically the derivative of this output with respect to this input. And thanks to the autograd functions, thanks to the physics-informed setup, this is something that we can do. So as I said, we are doing this now for a sequential pin setup. So at each stage in that level of the work, in that paper, at each loading increment, I'm training another new network, another pin to predict what's happening. And these were the preliminary results. So the first column here, these are the true results. And these are the finite element, these are the neural network predictions. So this is the true non-local strain, this is the predicted non-local strain, and that's the error. And then this is the damage that's computed in the true versus the predicted case, and that's the error. But then this is the interesting part. Here I'm showing the conversions of the finite element versus the I-FENN setup. And as you can see here, while the finite element in this case converges in 12 iterations, the I-FENN converges in 5 iterations. And the reason is simply because the neural network that we have trained already has an idea about the answer. So the neural network is not only helping us reduce the number of variables in the solution vector, the number of unknowns in the solution vector, but also it's helping the advancement of the nonlinear solver. So we have remarkably low errors. We have a good solver conversions. But then this, just once we tried that opened the Pandora box of questions. What are we going to do next? There are multiple things that we want to do. Number one, where do the savings come from? Why is this more efficient? Number two, can the pins be realized as a numerical method? Number three, can we, instead of training many networks, we need, at the end of the day, I need a model. I cannot just afford to keep training new networks for everything, and then it defeats the purpose, because then I need to know the answer before I can train. And then there are other generalizations in terms of the boundary conditions, the loading, and other things. So we'll tackle these questions one by one. Number one, where do the savings come from? As I said earlier, from solving a smaller system of equations. We can also train on a coarser mesh and predict on a finer one. So if you want to do a finer analysis, this is very useful because networks have a very good interpolating capability. And there are other ways also, by combining different physics and different models, that this I-FENN setup can be leveraged to show us more time savings. The second question is, can pins be realized as a numerical method? And this, with someone who has their background, my background is in finite element fracture modeling, this is a very important question for me. Show me the conversion, show me the numerical behavior. It's not just a black box that, I turn on and I start getting answers. So when we looked into the literature and what are the applied math people are offering, what we find is the universal approximation theory, which basically tells you that, as you take a large enough network, and if you train good enough and you have a big enough data set, you're going to converge. That's the theory. Now, in the practice, a lot of that is actually dependent on the optimizer. So we started asking some questions, and we wanted to see things for ourselves. Do they really converge? What are the optimal hyperparameters? In finite elements, we have some ideas about how to choose our element sizes, our time step sizes, and so on. What's the equivalent of that here? So I'm not going to go through all of the details. That's a separate paper on its own, and it's even that just scratches the surface. But we started doing some empirical analyses, and we established some performance metrics to look at that behavior. And long story short, we saw that our network converges well. So, as we go to larger networks, the errors decrease. As we train further, also the errors decrease. We found an interesting thing here, which kind of matches what we see in finite element, that, in some cases, it's the best combination in terms of the combination of error and the computational cost is to use square networks, that being that the number of layers is equal to the number of neurons per layers. This is an empirical finding for this specific model. There is, we didn't take the time or the effort to look into it further to see if we can formalize this using a mathematical theory, but we confirmed that for the model that we're working on. But I would really love to see more research into establishing this as a more robust theoretical guideline for people on how to optimize hyperparameters. Right now, many applications just use things like hyperopt or additional packages to optimize the hyperparameters of the network. And then the biggest question for us was the role of the optimizer. So in some cases, when you use specific networks that are 2D,